Hi all, this is Mr. Yeager for chemistry, and we are now looking at some of the acid-base calculations that we have to do in this unit. This is the majority of them. The only thing I still got to show is titrations afterwards, but this is a lot of basically 1 to 2 step type problems that you got to be able to work through. That shows us the again, acidity or basicity of the solution itself, so it can help us identify whether we have an acid or base solution. And then we're also going to be looking at equilibrium again. There can be equilibrium situations with neutralizations or ionizations in terms of how many particles are formed, and it's creating the forward inverse reaction. Okay, so what do we do to calculate? What we're going to calculate, I just basically said this, is we're going to calculate out concentration of H+, which can be H3O plus. It's the same idea. The hydrogen hydronium ion is the acid ion. And then we also want to find the concentration of OH minus. We'll also calculate pH and POH. Those two things kind of all go together. And then separately from that, we have Ka and Kb. Okay? So for concentration, all right, as we already talked about, acids and bases is mostly about how much H plus and OH minus is in solution. If you have a concentration of H plus larger than OH minus, your solution is acidic. It should have a pH less than 7. If you have less H plus than OH minus, your solution will be basic. It'll have a pH greater than 7. So how can we basically figure out how much, H plus and OH minus is in the solution, essentially? Well, we go back, actually, take a step away from that, and we talk about something called the self-ionization of water. Okay? Water is actually all the time undergoing a change between the liquid water, H2O, into its ion forms. It's splitting up into H plus and OH minus. And so there's an equilibrium occurring there. Now, there's a very large, I'm going to say that, but there's not a lot of H plus and OH minus forming, but there is still developing that amount inside the solution itself. This is called the self-ionization of water. It's ionizing into its own parts by itself. It turns out that the concentration of H plus and OH minus, when water is the only thing present, is 1 times 10 to the negative 7th molar for both H plus and OH minus. Okay? So those actually are very important numbers. It turns out that is exactly how much H plus hydrogen ions and hydroxide ions are present in water at all times. All right? Based on those numbers, we can then create what's called the equilibrium constant for water, which we call the Kw. So this is, again, created the same way we created any of our equilibrium constants last unit, or in the equilibrium unit if we're doing that afterwards. Okay? And so that gives us, I'll show that real fast. It's the whole idea that you have H2O liquid producing, let me just do that, sorry, that way and that way, producing H plus aqueous plus OH minus aqueous. And so if I create the equilibrium equation for it, it would just be Kw, water, is equal to H plus concentration over times the AOH minus concentration. Water's not in it because water's a liquid, and we don't include liquids or solids. So if I multiply those two numbers together, the 1 times 10 to the negative 7th times 1 times 10 to the negative 7th, the value of Kw is 1 times 10 to the negative 14th. So that leads us to our first formula, that Kw will equal H plus times OH minus concentrations. I can just put those two things together, all right? So if I multiply H plus and OH minus, I know I have Kw, and Kw is a constant now. So you always know Kw is 1 times 10 to the negative 14th, okay? All right, so that is one way we're going to use some of the problems. We'll go back, I guess I'll show you that real fast. Might as well show you an example problem, okay? Not that one, this one, all right? So with this example problem, okay, you can see my first few problems here. It's very repetitive. That's why we're kind of looking at it here. It says calculate H plus. You have a hydroxide concentration of 1.0 times 10 to the negative 4th molar. So what you would do is, we're going to use, I'm not going to rewrite the formula. This formula right here, 1 times 10 to the negative 14th is equal to H plus or times OH minus. And so that would be 1 times 10 to the negative 14th equals concentration of H plus times 1 times 10 to the negative 4th. And so all I would do is divide that over to the other side. And so I get 1 times 10 to the negative 10th molar is my H plus concentration. You will absolutely keep these in scientific notation. Okay? So 1 times 10 to the negative 10th molar. But that's basically it. I mean, there's nothing too special with that formula. I mean, I have another one. Again, it's all the same idea. 1 times 10 to the negative 14th equals H plus times 6.5 times 10 to the negative 12th. I divide that to the other side. Okay? We're always solving for one of the concentrations. If I was solving for OH minus, I'd be giving you the H plus. This one comes out to 1.5 times 10 to the negative 3rd molar. Okay? So that's basically it. And I can compare the two. I mean, that would be one of the other things I would look at is I go, here's my H plus concentration. It's to the negative 3rd, my OH minus to the negative 12th. So which one do I have more of? The smaller the negative, the larger the decimal. So I have more H plus, so this would be an acidic solution. This solution would be an acid. All right? So I could compare them at the end, which is definitely something we would do. Whichever one I have more of, that's the type of solution I have. In the first problem here, I have more base, so this is a basic solution. Okay? So that's that first equation. All right? We're going to be kind of coming back and forth a lot here. Ugh, wrong button, sorry. There. pH and pOH. So we talked about this already a little bit, but not too much. pH is what's called the acidity scale. It is a little bit weird that we're basically saying the lower the pH, the stronger the acid. All right? And again, we've already hammered that sum. The idea of less than 7 pH is an acid. Greater than 7 is something that's basic. All right? But the lower the pH, the stronger the acid. We generally say the pH scale runs from 0 to 14, but please understand there is such a thing as a negative pH, and there are pHs that can get above 14. We just generally keep the scale between 0 and 14 for most of high school. If you take a college chemistry course, that pH scale can go wherever it wants to go. All right? We know a pH of 7 is neutral. But one of the big things to get off a pH scale is the pH scale, with every 1 change in pH, means a 10 times change in strength. And we're going to see why in a moment. So a pH of something that is 3 compared to 5, the pH of 3 is 100 times stronger of an acid than 5. So every little change in pH actually makes a pretty significant difference. We can see that in the soil, where certain plants can only live in a very small range of pH, because what's actually happening is they're living within a very large concentration of H+. And if you go above or below that, it becomes too strong or too weak for it to survive. So 1 change in pH is a 10 times strength. So every single time you go up by 1, you multiply by 10. Okay? The difference between 1 and 14, I mean, that's in the trillions, quadrillions in terms of the difference in strength. Ultimately, pH is measuring concentration of H+. That is really what pH is really telling us in the end. It's how much H+ is in solution. And it ends up being a logarithmic scale. The whole point of log, as you might have learned in math, or if you haven't learned yet, is logarithms basically make very large and very small numbers into something very manageable, very counting oriented. So pH is simplifying those the complex concentration values. So like we saw, 6.7 times 10 to the negative 4th molar. What does that mean? The pH scale is going to make that much easier for us to see what type of solution I have, acid or base, because it's going to come out between 0 and 14. Okay? So there's our formula. pH is negative log of H+. There are no units. all right, unlike concentrations, molarity. And we got to be able to use the logarithmic function. You can see it's negative log, okay? pOH, we also have what's called a pOH scale. That's basically the same idea, except it's now measuring the amount of OH minus. Again, P in front of things is basically saying take the negative log. That's really what the P is. There's things like we could say pKW, and then we take the negative log of the KW and solve for it. So P is just standing for take the negative log of this concentration of this value that you have. All right. pOH, we have to be careful, is opposite in terms of what's basic and what's acidic, because it's measuring pOH. If it's less than 7, we're now basic. If we're greater than 7, it's acidic. So it's the opposite scale of the pH scale. All right. That leads us to kind of our last formula for this particular part, where simply pH plus pOH will equal 14. All right. pH plus pOH will equal 14. So we got 4 formulas here. We have our KW, we got pH, we got pOH, and then we got pH plus pOH is equal to 14. So those are all the formulas we have for these initial acid-base calculations. So if I go back and show a few more problems with this then, and because there's one thing I got to kind of go around and show. If I do this next part, just kind of illustrating these, okay? It says calculate the pH. Okay, we got to pay attention. That's only going to work for hydrogen. Remember, pH is equal to negative log of H plus. There's really no showing your work. I mean, you show me you plugging everything in, but there has to be the final answer then in the end. So the first one, pH would equal negative log of 5.4 times 10 to the negative 5th. I plug that into my calculator, and this comes out to 4.3. Done. That's it. Your answer is 4.3. I can now ask you, do you have an acid or a base? Well, it's less than 7, so this is acid. All right. I'll jump to number 8, and then I'll show you a hydroxide one. All right. Number 8 says 2.8 times 10 to the negative 6. So negative log of 2.8 times 10 to the negative 6. Plug that in exactly as it is in your calculator. Don't forget the negative sign. And guess what? You get 5.6. That is also an acidic solution. Not as strong as the other one we just did, almost 10 times weaker, but it is 10 times weaker, but it's still an acid solution. So let's show off a little bit with the pOH, or what would happen in some cases. This number 7, it says it has a hydroxide concentration of 8.7 times 10 to the negative 9th. So if I do pOH, big mistake is people just sit there and go negative log, negative log, negative log, negative log, and they don't read it. If I'm doing negative log of the hydroxide, I'm getting pOH. So I would do that, 8.7 times 10 to the negative 9th. Okay? And that should come out to, so I'm doing a little bit of this in my head, that should come out to basically 8.1. The pOH would equal 8.1. 8.1, not 8.1, I think 7. Sorry, let me try to figure that out. Yeah, no, 8.1. 8.1. Okay? So we can already see pOH is greater than 7. This is an acid solution. I know that's confusing, but when the pOH is greater than 7, we have an acid. Again, we want low numbers for pH and pOH. But the question was find the pH. So all I do now is I just go 14 equals pH plus 8.1, subtract 8.1. And my pH is equal to 5.9, which also supports that it's an acid. Da-da. Okay? So that's basically the majority of these initial calculations. We just have to be very careful and go, am I looking at hydroxide or am I looking at hydrogen? Okay? So you can see I have some pOH problems. We do the same thing. What I want most of you guys just to recognize is we can use these 3 formulas to get to whatever I need. The way I always look at this is, or these 4 formulas, pH equals negative log of H plus, pOH negative log of OH minus, and and then pH plus POH equals 14. All right? You have these four formulas. You should never have to do more than 2 steps to get an answer. Every single problem you get with pH or concentration of H plus or OH minus or POH should either be a 1-step or 2-step problem. If you're doing any more than that, you're making your life super difficult. All right? So the way I always look at it is go, what are you given? What are you solving for? Are they in the same formula? Like, I'm not going to solve for this one, but it says, what's the concentration of hydrogen? Actually, we will solve for that one in a second. What's the concentration of hydrogen ion if the pH is 1.8? Well, I have pH and I'm looking for hydrogen. Guess what? I have a formula that I can do that in 1 step. Now, I do have to show you how to rearrange it, but we'll come back to that. Okay? If I have, what's the concentration of hydroxide if my pH is 13.2? Well, now I do not have these 2 things in the same formula. Okay, pH and OH minus do not show up in the same formula. So it's your choice. You have 2 ways you can go, but it's going to be a 2-step problem. I'd recommend plugging this into the pH plus POH equals 14 formula. I love making people try to use that formula because it's the easiest formula. So you do that, you find the POH, and then guess what? You can then get the OH minus concentration with the POH formula. Okay? Do we have to do it that way? No. We could have gone and found the hydrogen concentration first and then gone to the top formula and found the OH minus concentration. So there's all different ways to kind of go through this. Okay? But again, it should be no more than 2 steps. Now, 2 other things. If you see that you're given an acid or a base, these are always versions of a strong acid or a strong base. I would not be giving you weak acids or bases in this problem. That's for Ka and Kb in a moment. All right? They're always equal strong acids or bases. Well, if we recall, a strong acid or base completely ionizes into its ions. And so what that means is, if I'm looking at this one right here, 12 molar HCl, HCl will change into H plus and Cl minus. If I have 12 molar, all of that will change into 12 molar H plus. It also changes into 12 molar Cl minus, okay? But all I'm really needing is the concentration of H plus. So in that problem, the concentration of H plus is 12 molar. So this is just kind of like adding just a little bit more depth to it, where you don't have to really overthink it. If I give you a concentration of an acid, that's H plus. If I give you the concentration of the base, that's the concentration of OH minus, the hydroxide. Okay? So last thing to show, at least in this particular part. What if I get a problem like number 21? It says, what's the concentration of hydrogen if the pH is 1.8? So that, again, like I said, should be a 1-step problem. Okay? Oh. All right. So this comes back to, do you understand a little bit of what logarithms do? Okay? A log in your calculator is always log base 10. Again, what the pH is doing is it's telling you what is the exponent you would raise 10 to get your number, to get your concentration, essentially. So the way this kind of reverses, and again, you can just remember my final formula and memorize that. I don't usually give that to students. They have to kind of figure that out on their own. But if I said, let's try to figure out the H plus, because I have the pH, okay? I'll even put the number in there. 1.8 equals negative log H plus. I cannot just divide the log over. That makes 0 sense. Well, what I do technically is I'm dividing both sides by -1. I'm moving the negative sign to the other side. So now I have negative 1.8 equals log of H plus. And this is where the log base 10 comes in. Basically what we're saying is 10 raised to negative 1.8 is equal to the concentration of H plus. So what happens is I do 10 to the negative 1.8, and that will get me my concentration. All right, which in this case equals 1.6 times 10 to the negative 2 molar. Okay? So that's where I would rearrange this for pH. What did I ultimately do, if you can see what happened? Basically, the concentration of H plus is 10 raised to the negative pH. So if you want to copy that formula down as you're watching this video, if you need to rearrange the pH formula, H plus is equal to 10 to the negative pH value. OH minus is equal to 10 to the negative POH value. So if I go and look at another one real fast, let's see if I see one here. It says it right here. What's the concentration of hydrogen if the pH is 8.9? I would do concentration of hydrogen equals 10 to the negative 8.9, and I would plug that in and get my answer. Again, in this one, if I can find it quickly, I got 1.3 times 10 to the negative 9th molar. Okay? So that is all of the initial pH calculations. So one other thing I want to show you, I know we're going a little bit long in this video, is we also want to go back to Ka and Kb, our equilibrium constants. So it's the same formula as we did before with equilibrium. Okay? K is equal to the products multiplied together divided by the reactants multiplied together. All right? The usefulness of Ka and Kb is they show us how strong the acid or base is. So this is a way we can distinguish between strong and weak acids. Generally, Kas that are close to or higher than 10 to the negative 2, and again I mean 10 to the negative 1 or whole numbers, they are strong acids and bases. If your K or Kb is less than 10 to the negative third, that generally means you got a weaker and weaker acid or base. Okay? So we basically have to just go back and show this sum again. So if I go to this one now, all right, we basically do dissociations here. So I'll do a couple of these problems, and then obviously you got to practice more on your own. Write the dissociation and Ka equation for benzoic acid. So this goes back to like the ionization things that we did. So we got H, HC6, H5, CO2. That's going to separate out into, and technically it's an equilibrium now, we're going to do that, H plus C6, H5, CO2 minus. Okay? Is what we got there. Now in this case, we are saying all of these things are aqueous. This is aqueous, this is aqueous, and this is aqueous. With that in mind, still looking at this first problem, the Ka value for it would be the concentration of H plus times the concentration of C6H5CO2 minus divided by concentration of HC6H5CO2. And that would be my Ka value I would solve for. You could see where we might give problems where I give you the pH. You can see that farther down. I'll try to maybe do two problems and then I have to show you one ice one, but it's the same idea as we've done before. Is we can find the H plus concentration and then we can calculate the pH or the OH minus or the POH or anything we've done before. But we're using those again. So I'll do this next one, and a lot of these are pretty straightforward. We don't get too in depth with these. But it says the H plus of a 0.01 molar solution of cyanic acid, so this is 0.010, is 0.0010. That means the other compound is also 0.0010. If this form 0.0010, the other one does too. They both form it together, okay? Since it's all 1 to 1 to 1, all right? And again, most of the time that's all we're looking at because we're mainly going to look at only monoprotic acids, all right? So if I wanted to then calculate this out, the Ka value would be 0.0010 times 0.0010, the products, divided by 0.010, all right? And I get for that one, 1 times 10 to the negative fourth. Ka equals 1 times 10 to the negative fourth. That shows that this cyanic acid is not a particularly strong acid. It's a bit of a weak acid. But that's it. Let me show you the next one, number 3. If I do number 3, a solution of 0.0050 of butyric acid HC4H7 has a pH of 4.0. Calculate the Ka. All right, so again, Ka, I'll already write that out. going to be concentration of H plus times concentration of C4H7 minus divided by HC4H7. Okay? So, I know my concentration is 0.0050 molar. Let's figure out the pH is 4.0. Okay? So that would be where I do 10 to the negative 4, and that actually equals 1 times 10 to the negative 4th molar of H plus. Because that's how much H plus is formed, that's the same amount that C4H7 is formed. Sometimes you might see that we just do this. We just square that number. 1 times 10 to the negative 4th squared, because I'm multiplying the same number, divided by 0.0050. That gives me 2.6 times 10 to the negative 6. Is that right? Yep. 2 times 10 to the negative 6, not 2.6. And there you are. That's your Ka. All right. So, I mean, big things to see there. However much H plus is formed is the same as the other ion. They both form the same amount, being monoprotic, and they have to have 1-to-1 ratios of solutions of molarity. So that's where we just got to be careful with that a little bit. All right. Let's try an ice chart problem. You can see I will tell you when you need an ice chart. Okay. So let's do this one right here, number 7. Okay. For number 7. We have my reaction. I got to write it out first. C2H5NH3. It's going to produce, it's a base. Okay? It's a weak base. What that means is I'm going to form, if I react it with water, okay, I'll actually have to fill this all out for you. This is aqueous. I put it in water. And what's going to happen is it's going to be C2H5NH4 plus OH minus. This is all aqueous. All right, because I gave you a base one, we actually have to add the water in, so we see that the OH minus comes on out there. Okay, we have to see that. Okay, so this one again is a little bit tough. This will be a bit of a problem to go through. We can basically ignore the water because it's a liquid, so it's not going to affect our equilibrium. But in this case, it says this is a nice problem. That's because not that or enough of this will ionize that will significantly pull away from the concentration of my initial amount here, the C2H5NH3. So, if it has an initial molarity of 0.0024 molar and a pH of 11.53, what is the Kb at the end? So, I'm saying this is 0.024 molar. Okay, 0.024 molar. Well, I can figure out, sorry, let me write this out, ice or rice. Okay. This one's not going to be used at all. There's my middle. Okay. I start out with basically 0 and 0 of these. I need to find the change. So, I can figure out, based on the pH being 11.53, okay, essentially I can say the H plus, if I take this, I could do 10 to the negative 11.53, that'll equal 2.9 times 10 to the negative 12 molar. Then I could do 1 times 10 to the negative 14th equals 2.9 times 10 to the negative 12 times OH minus, and that gives me my OH minus being 3.4 times 10 to the negative 3rd molar. So that is how much is at equilibrium here, 3.4 times 10 to the negative 3rd. So that's how much was added. 3.4 times 10 to the negative 3rd was added. 3.4 times 10 negative 3rd was added of the other ion. And that's how much was subtracted, minus 3.4 times 10 to the negative 3rd. That leaves me with a final concentration of, equilibrium concentration of my initial reactants of 0.0206. And then finally, my Kb, B standing for base, because I'm looking at it for the OH minus, would be 3.4 times 10 to the negative 3rd squared over 0.0206. And that is 5.6 times 10 to the negative 4th. Okay? And there we go. So that's as complicated and crazy as it gets. It's similar to what we've already done. So again, it's really not anything special. You can see again, I have to write down what I start with my ice chart. Okay, I know it's a little bit messy, but you can see that all my changes are the same. I'm subtracting from the reactant, adding to the products. The products get the same amount. I figured out how much OH minus I had by using the pH, converting it to H plus and then to OH minus, and then plugging it in, subtracting as needed, and solving. So that's 5.6 times 10 to the negative fourth for those. So that's how we approach any of the ice problems. If it doesn't say use our ice, that this is an ice problem, you don't have to worry about doing that. So like the next one says, don't worry about doing that. Okay? There's supposedly like a 5% rule where if it doesn't change the amount by 5%, we generally don't have to do an ice problem. If we do change more than 5%, we need an ice problem to make sure it's clear. So that's everything. It's quite a bit in terms of math stuff to do, but it's a big part of this particular unit. And all we got left now is titrations. So thank you very much. Stay well.